The plan is to discuss what is known as Clausius inequality, and I'm going to prove this. Okay. So what is this Clausius inequality? So first let me write down this. The Clausius inequality says that for any cycle, this inequality holds good. So for any cycle, this inequality holds good. This is what is known as the Clausius inequality. Okay. Let me write down this. For any cycle. For any cycle means either for any cycle, meaning either the reversible cycle as well as the reversible cycle and the real cycle, that is the irreversible cycle. So for both the cycles, this inequality holds good. Okay, so Clausius inequality is cyclic integral of del q by t is always less than equal to 0. So the plan of today's lecture is to prove this inequality. Okay, we will be proving this inequality. So proof is what I am going to discuss in today's lecture. Okay, and to prove this, I need to refer to what is called as the Kernel Theorem. Okay, so let me rub this and write down. Okay, now it is clear to you that what is to be proved. It is to be proved that cyclic integral of del q by t is less than equal to 0, and this expression is known as Clausius inequality. Okay, so the plan of lecture is to prove this inequality, right? And my starting point is I would be starting this discussion, which I had already started by a poll question, by referring to the famous theorem, namely the Kernel theorem. Okay, so let me first, to prove this inequality, I will be referring to what is known as the Kernel theorem. So what is the Kernel theorem? So let me first write down what is the Kernel theorem. So Kernel theorem says that no heat engine can have an efficiency greater than the Carnot engine. And the Carnot engine. So the Carnot theorem says that no heat engine can have an efficiency greater than the Carnot engine, while they are operating between the same two temperature reservoirs. Okay, so source is one reservoir and sink is another reservoir. Okay, and making use of this fact, making use of this Kernel theorem, we would be proving the Clausius inequality. Okay, so I would be using the Kernel theorem to. So this is the agenda now, or working between the same two temperature reservoirs. Okay, so this is this one. Okay, this one Kernel is at highest efficiency. Okay, so now let us start with the proof. That is the proof for Clausius inequality. So let me rub this. Okay, so now we are going to discuss the proof of Clausius inequality. Proof for Clausius inequality. So it's very simple proof, so don't be afraid of this. So what we are going to do at the outset is we would be considering the reservoirs. Okay, as I said that let us say this is your source. Okay, source, and let us say that the source is at a temperature pH. Okay, and let us talk about the, let us say this is another reservoir, a sink, and let us say that sink is at a temperature TL. Sink is at a temperature TL. Okay, now let me consider, let me assume a Carnot engine operating between and a sink temperature TL. Okay, operating between source temperature TH and sink temperature TL means what? It means that this Carnot engine is accepting certain heat QH from the source, and this heat transfer is reversible heat transfer. This heat transfer is reversible heat transfer. Okay, and this Carnot engine is rejecting certain heat, let us say QL, and again this heat transfer is, let us say, a reversible heat transfer. Okay, by reversible heat transfer, what I mean to say is that when the heat is being accepted, okay, accepted by the working fluid of this Carnot engine, then this Carnot engine, let me draw it as like this is Carnot engine, then this Carnot engine working fluid is accepting the heat at a temperature which is almost at TH. Okay, it is slightly less than TH, but this is almost at TH. Okay, so it would be slightly TH minus some DTH. Okay, and this DTH is almost zero. Okay, so we can as good as say that the working fluid is accepting the heat at a temperature TH. Okay, so this is called as a reversible heat transfer, heat addition. Similarly, when I'm saying that this Carnot engine is rejecting the heat reversibly, the meaning is this temperature, the temperature at which the heat is being rejected. Okay, so this temperature is slightly greater than TL. Okay, slightly greater, because without which there won't be any heat transfer. Okay, and this again because it's a reversible heat transfer, it would tend to zero. Moreover, so this is called as a external reversibility. What we are talking about is a external reversibility. This Carnot engine is externally reversible in the sense that the delta T between this is almost zero, and delta T between this is almost zero. Okay, so this delta T is almost zero, and this delta T is also almost zero. Okay, this is the meaning of external reversibility. Now this Carnot engine is also internally reversible, and because it is internally reversible, it is going to produce the maximum work. Okay, let us say it is going to produce the work equal to WC. Okay, so WC, or let me call it as WC, right? So WC is the work output of the Carnot engine. Okay, so this is one engine we had considered operating between a source temperature and sink temperature. Now let me consider another engine. Let me choose some other color for this. Okay, let me consider another engine which is now a irreversible engine. Okay, which is now an irreversible engine. This is an irreversible engine. Okay, so this engine is an engine working on some thermodynamic cycle, and this engine is an irreversible engine, or it is a real engine. Okay, and what it is doing is this engine is accepting the heat. From the source. Okay, so it's accepting the heat from the source, and let us say that it is accepting the same quantity of heat QH. This engine is also accepting the heat QH. Okay, QH. Okay, this is just to ensure that the input is same, right? And for comparison sake. And let us say that this heat transfer is also reversible. This is also a reversible heat transfer. Okay. Now this engine is an irreversible engine, and let us say because it is a different engine now, it is an engine, so the heat rejection would be something else. And the work output also would be something else. Okay, so let us call this as WI. Okay, WI. So this irreversible engine is also accepting the heat QH from the source irreversible engine. The Carnot theorem says that the efficiency of the Carnot engine is greater than efficiency of the irreversible engine, and put upon input. So it means that the efficiency work upon QH would be greater than work I upon QH, right? And because this is same, the work output is greater than the output of the efficiency of Carnot is greater than efficiency of irreversible. Efficiency is work upon heat supplied. Heat supplied we are keeping it as same. So the work output of the Carnot engine is greater than the work output of the irreversible engine. Now, what is the work output of the Carnot engine? From the first law of thermodynamics, the work output of the Carnot engine is QH minus QL. That is the first law of thermodynamics. Okay. So this would be greater than, what is the work output of the irreversible engine? It is QH minus QL dash. Okay, this is from the energy balance. You see that energy balance, if you look at this, so WC is equal to QH, heat supplied minus heat rejected. Similarly, WI would be heat supplied minus heat rejected. Okay, so from this, what it means is that QL is less than QL dash. Okay, it follows that QL is less than QL dash. Okay, so this is one. Let us call this as some equation 1. Okay, so from the Kernel theorem, now we have got an insight that this heat rejected would be more, obviously, because the efficiency of the irreversible engine while operating between the same two temperature reservoirs is less as compared to the Carnot engine. So the heat rejected would be more. Okay, now let us go to the cyclic integral of del Q by T. Okay, so what we want to prove is the inequality. Okay, so now I will be rubbing this. Let me rub this now, and let me calculate the cyclic integral. Let me calculate the cyclic integral of del Q by T for this engine, for the irreversible engine. So cyclic integral of del Q by T for the irreversible engine would be what? It would be QH upon TH minus QL dash upon TL dash. Oh, sorry, TL. Okay. We are assuming that this heat transfer is also reversible. Okay. So this engine also is externally reversible, but this engine is internally irreversible. Okay. So this engine, this is for convenience we are assuming, because I wanted to use the same TL. Okay. Otherwise, I would have used a different TL, and that would have made a bit complicated proof. Okay. So for the simplicity, I would say that the heat rejected is also reversible, heat supplied is also reversible. However, the engine is internally irreversible. Okay. So for this, QH by TH minus QL dash by TL would be the cyclic integral of del Q by T. So let us call this as equation 2. Okay. Now let me apply the Clausius theorem. Okay, not inequality. Clausius theorem to the Carnot engine, to the reversible engine. Now, what do we understand? What is the Clausius theorem for the reversible engine? Clausius theorem, not inequality, mind well. The Clausius theorem for the reversible engine is what? It is cyclic integral of del Q by T. Del Q by T is equal to 0. But what is cyclic integral of del Q by T? It is QH by TH minus QL by TL, and from, because this is a reversible cycle, which cycle? This Carnot engine. Okay, the first diagram. Okay, this is a reversible cycle. So according to Clausius theorem, cyclic integral of del Q by T for a reversible cycle happens to be 0. Happens to be 0. Okay, this is your equation 3. Equation 3. Okay, so now look at this equations 1, 2 and 3 very carefully. Look at this equations 1, 2 and 3 very carefully. You will find that this term is greater than QL. Okay, and when QL, then because for a reversible cycle this becomes equal to 0, this becomes equal to 0, right? So if you are putting some other value, okay, which is greater than QL, look at it from a mathematical perspective. Okay, so if I am putting some value which is, then it becomes negative. So when I am putting, now you know this is the equation 3. You know this is equation 3. So this equation 3, if you compare it with equation 2, because this QL dash by TL, okay, it has to be negative. Okay, has to be negative. But what is this? What is this? This is nothing but cyclic integral of del Q by T for a irreversible cycle. Okay, so let us call this as equation 4. Let us call this as equation 4. Okay, so what is equation 3 and what is equation 4? So equation 3 says that cyclic integral of del Q by T, if it is a reversible cycle, that is equal to 0. That comes from the Clausius theorem. And what is equation 4? We have proved this, that cyclic integral of del Q by T, if it happens to be an irreversible cycle, then the cyclic integral of del Q by T will be less than 0. It means that that value would be negative value. Okay, combining this two, that is combining the Clausius theorem with this equation 4, we can write a famous inequality, that is cyclic integral of del Q by T, is less than equal to 0 for any cycle. Okay, so this is known as Clausius inequality. Okay, this is known as the Clausius inequality. So this inequality is valid for the reversible cycle as well as irreversible cycle. When the cycle is reversible, then the equality holds good. When the cycle is irreversible, then the less than 0 sign holds good. Then the less than 0 sign holds good. Okay, that means if it is the reversible cycle, then cyclic integral of del Q by T will be equal to 0. And if it is an irreversible cycle, if it is a real cycle, then the cyclic integral of del Q by T will be negative. This is now a very important tool. You try to understand that this is a very important tool to decide whether the cycle is reversible or irreversible. Okay, so the Clausius inequality helps you decide whether the cycle is reversible or irreversible. If you do the calculation for a given engine, and if you find that cyclic integral of del Q by T becomes zero, then you can say that the engine is a reversible engine. If you find that the value comes negative, then you should say that the engine is an irreversible engine. One more thing, and this is a very beautiful thing, it is, if it is more negative, it will be more irreversible. What is the significance of Clausius inequality? The significance of Clausius inequality is that it is now bringing up the quantitative parameter